It's always really impressive when your slides just actually appear for you. So first of all, thanks to SIGSOFT, thanks to the awards committee, thanks to my nominator and supporters. It really is a privilege to receive this award. And I'm actually going to step out of my comfort zone in this talk because I'm not going to talk at all about the research that led to this award. What I want to do is spend just a few minutes thinking and considering about whether our community is actually asking and answering the questions that we should be to build the software that's highly responsive, highly reliable, of high quality overall, that is able in a sustainable way to meet the needs that humanity has for software. And I'm going to contend a little bit that maybe we're not doing enough about asking and answering those questions in this community. And what better community to be thinking about that than our community? So hopefully I've got the right clicker. I do. And so in this talk, I'm going to rely a lot on a lot of the words of wisdom that a luminary of our field that we lost last fall spoke about, based on his experiences with building IBM OS 360 and other kinds of systems, and being able to eloquently tell us about some of the difficulties that there are in building software systems. So one of the quotes from Professor Brooks is that software work is the most complex that humanity has ever undertaken. And we can argue whether or not that's exactly the case. Is it the exact most complex? But I think together we can agree that software is pretty darn hard to build. And so when we're building it, are we actually spending enough time in our community thinking about that complexity overall? How hard it is to build these systems? And how hard it is to build it in a time where we have so many needs upon us to be able to provide the communication, the software that helps us communicate, the software that helps meet and address people who might have needs to be able to live because they have disabilities of some sort, to be able to build the software that runs our infrastructure, or to be able to build the software that lets us have fun by playing things like video games. So here's the last slide that I'm going to have for my talk. I want to talk a little bit about the essential complexities that there are in building software, reminding us of what those are. Many of those come, of course, from Professor Brooks. And I want to add a fifth kind of complexity that I think is essential, which is the complexity about context. So I'll explain what that means. And I'm going to try to give you a couple of ideas about how in this community we might change what we're doing to better address some of those issues. And in particular, I want to talk about some ways that we might actually think about the holistic problems of building software rather than getting too focused on individual, very detailed parts of software development. I'm not trying to say that we should stop all of that kind of work. It's really important. We've heard great talks today. But we might need to broaden what we're doing as a community to think about the problems more holistically. So the talk is divided into two parts. I want to talk a little bit about what I mean by complexities and by the fact that these complexities have to be solved in the context of wicked problems. And I want to talk a little bit about potential paths forward. So let's delve into the first part. So here's a bit of a timeline. Hopefully most of you are familiar with the No Silver Bullet paper, Essence and Accidents in Software Engineering, which was an invited paper that Fred Brooks published in 1986. It's hard to, in a quote, capture the richness and depth of that paper, but I tried to put one of those quotes on the screen. And what he was looking at in that paper was the fact that there is always something new coming up that, to some extent in our field, purports to solve all the problems, or many of the problems that a field is facing. So the quote is, "But as we look to the horizon of a decade hence, we see no silver bullet to really solve the essential complexities. There's no single development in either technology or management technique which by itself promises even a one order of magnitude improvement in productivity and reliability and in simplicity." And if you think about this in 1986, this is when hardware was rapidly advancing each and every year. And so there was a lot of questions about, can software keep up? Now, I put the timeline at the top to kind of remind ourselves that this 1986 paper, and if you're not familiar with it, suggest that you download it and maybe read it on the likely long plane ride that you have home. That 1986 date That's only about 20 years since software engineering kind of started to be talked about as software engineering from the 1968 NATO conference. 10 years after publishing that 1986 paper, there was a lot of feedback that apparently Fred Brooks was receiving about the ideas that he had published. And as part of his retrospective book, he included an essay called No Silver Bullet Refined 10 Years Later, where he concluded that indeed he hadn't seen any of those advances that had been purported actually change the amount of productivity we got in software. So what were the complexities he talked about? Well, there was really 4. He talked about complexity itself, so a little bit of a recursive concept going on here. And he said software is complex because no 2 parts of it are alike. We need a lot of parts to build something that matters. And we have this thing called abstraction that we use so that if 2 parts are alike, we combine them in together. Even with that powerful concept, we still have a lot of parts that get put together to build the software, and as a result, it's very complex. A second complexity he talked about was conformity. If you're building a system that especially is going to interact with hardware components, what is always going to be asked to change? It's not the hardware, it's the software. If you're building a system that's going to go out and be used by people, what changes? Not the software, the people change. And I'm going to come back to that point later. The related complexity to that is changeability. Because of its ability to conform, software is continually getting bombarded to change. Even if you have a requirement that was specified, by the time that you try to develop it, sometimes people have tried to change that requirement even before you've been able to deliver it. So the fact that it's infinitely changeable means it's constantly under this bombardment to try to meet the needs of its users. And finally, an interesting concept given David's talk is, and I think you probably have some things to say about this one, is the fact that he referred to software as being invisible. And certainly there are techniques like state charts that help us think about software in a more visual way, but they don't necessarily apply to every kind of software development. They don't necessarily have been adopted by every software development company. And so as a result, we're still in a stage where often the software that is being built is considered to be invisible, and we can debate whether it's unvisualizable overall. If you walk into many software development companies and you ask the developers, what does the software look like? You're going to get different responses. If you ask the management teams overseeing those developments what the software looks like, you probably won't get any answer at all. I also want to argue that there's actually a 5th kind of complexity that we're now dealing with here in the 2020s, and that's of context. Now, context is really hard to define. So let me give you maybe 3 different kinds of context that we need to pay attention to. And one is the build context we're in today. So way back in 1986, one of the hype, the things that were on the horizon that might help was software reuse. And one of the things we've actually gotten good at is software reuse. There's a lot of open source out there that, in fact, development teams rely on each and every day. And those software supply chains that now make up the software that is being produced are getting longer and longer and longer. And we know that the brittleness of those software supply chains is pretty high. If you remember the left pad incident of a few years ago, a tiny piece of software that almost nobody knew really existed in the node systems ended up taking down the internet when it got pulled from that supply chain. And we know from Sonatype and other kinds of reports that the top 10% of the most downloaded open source projects have the most security vulnerabilities. So we're able with this reuse to build better and bigger software, but at the same time, we're actually in a very brittle state because of the way that we do build it. Now, another kind of context that's important is what I'm going to call deployment context. Another one of the hopes for a silver bullet back in 1986 was the idea of cloud-based systems. If you think about the 80s and you wanted a finance system, each and every organization that wanted a finance system would go to a consultancy or some software development company and ask for a finance system, and they would get one built. It would be deployed to them, they would put it on premise, and they would use it. And they knew what that software mostly did. What we've been able to move to now is to be able to build systems that we deploy on the cloud and have multiple organizations use their own instance of that same underlying system. To make it conform to what an organization needs to do, there's usually a big config, organization, charts, files that help tailor the actual functionality of that system to the organization that's using it. And this is great, right? This is one of the cases where humans now have to change more to the system because you're told, well, we bought this system, it's on the cloud, we can't change it, the humans have to change it. But one of the things I wanted to point out that I think is a problem with this deployment context is it gets really, really hard for the developers of the system and the eventual people who use the system to understand what the behavior is of that finance system they're using. So one thing I get asked to do every year at the university is to attest that we're actually following appropriate financial controls over every research grant in the university, that we have 2-level controls and various sign-offs. When we had the old system that had been built for us, I actually knew that that was probably pretty much true. We've now gone to more of a cloud-based system with lots of config files, and honestly, I have no idea whether or not that's true. And I know based on anecdotes from different people in the university, it works differently for different parts of the university. And so as a user, I would like to be able to query that system and say, is this actually a fact that's true? Or I would like to be able to go to the developers and verify that. But that seems to be very difficult to do with these deployment contexts. And finally, we've talked about this a lot. I'm not going to spend a lot of time on this slide. The societal context that our systems run in has to start mattering to us. Not only are we deploying them with config files, but we're deploying them with data that might have been learned from that the developers have never seen. So in that instance, how are we actually going to go about thinking about whether or not the properties we built into the system as developers are really holding true out there as it's getting used? So I'm going to contend that this idea of context is a new kind of essential complexity, and one that our community in particular, whether it's build, deployment, societal, and probably other context issues you can come up with, is one that we have to start paying a bit more attention to. Now, I actually put in the title the fact that not only do we have these complexities to deal with, but it's also a wicked problem. So a wicked problem is about, the fact that you have something that is almost unsolvable because of the interconnected and tangled nature of everything that makes up that problem. And obviously, when we're doing software developments, and in particular in this community, we think a lot about the technical aspect. We've actually gotten reasonably good at thinking about all the artifacts that make up a system, how they're interconnected, how can we reason about this interconnected web, how can we think about properties that span the many technical pieces that build up a system that's deployed. That technical system is built by an equally complex interconnected web of people. There's developers, there's testers, there's requirements people, there's users involved in that web. And we have some work that thinks about the complexity of that, interconnections and how hard they are. But we don't have near as much work that thinks about the interaction. What are the appropriate organizational structures that we need to be able to manage all of these complexities when we have so many different pieces of technical artifacts, so many different people that are involved in the mix of actually developing it? So I think we have to pay more attention to that. So hopefully that lays the stage a little bit to say we've really got to think about how we are going to manage how hard it is to develop software, and to do so in a way in the context of the socio-technical instance that exists around it. So what can we do about it as this community? Well, we've got these essential complexities, and I bet if you go through a lot of the papers that are in the proceedings, you'll see something in the introduction that relates the problem in the paper to something that's kind of like one of these complexities. So I threw up a couple of example areas of software engineering research at a very generic kind of level. I'm sure we'll have papers again, probably have some here, that might ask questions about Stack Overflow. What should Stack Overflow questions be like? What might we learn about them? And in that introduction, it might say something about, to help developers change software better, we should da-da-da-da-da. If we have a new method for requirements analysis, it might argue that it's going to reduce the complexity of the software development by having a better specification to be able to rely on. Maybe if we have a paper about fairness testing, it's going to refer to changeability, and so on and so forth. You see time and time again some indication of a generic connection to these essential complexities. But I think we have to start going further. We have to start thinking about what we're not asking. Are we thinking enough about whether there's evidence after that initial appeal to an essential complexity about whether there's been impact over time on actually reducing that complexity? Do we need to actually follow the introduction of something like program repair to see whether there's benefits over time? What do those benefits look like? Do they look like what we anticipated, or are they completely different? And I think Professor Harrell did a really nice job of thinking back over time and seeing how things, his state charts affected things over time. And do we adequately compare these new ideas on large systems? Do we actually look at a particular technique that we're introducing and see how it worked out on 4 or 5 big systems? Over the last 30 years that I've been part of this community, I think we've gone an awfully long way in going from thinking about largely anecdotal system descriptions to starting to hone in on particular aspects of describing where we might have tried one of our new techniques. So today, if you read a paper, you might see some context description about the system that a particular technique was applied to. It might talk about the static and dynamic artifacts, like how many lines of code was it, how many microservices were involved in the system, and it'll probably tell you a little bit about the development context. How many developers were there? How many bugs were open in the system? Metrics like that. I think we need to go a little bit further. I think we need to start thinking about this context capture in a more holistic way. And so what if, as part of trying out our techniques in an open source system, we were able to describe a little bit more about the development context? Maybe we could say something about the requirements process at play in that system. Or maybe something about how many design artifacts were actually there and what they look like. Or what was the team size in terms of not just the developers, but everybody involved. Talk about a little bit more about what the system is so we can start to understand when the techniques that we're developing may or may not apply. I also think we need to do a lot more in situ study. This was actually a lot more common, I think, when I joined software engineering research 30 years or so ago. There was a lot more, perhaps anecdotal descriptions, but descriptions of how someone had worked on aircraft control systems, as Parnas wrote about, or as we heard this today, that there's been inspiration taken from. There was more descriptions of things like OS 360, et cetera. How can we do more of this in situ longitudinal studies of software, whether it's open or closed software, where we can better understand how a technique plays out over time and how it plays out within a particular kind of context? Now, this is not easy, right? This requires a lot of hard work in this community. It's really, really difficult to start thinking about how do we assess results that are going to only be seen over time. That would take us as a community looking at results differently. We might have to convince funding agencies to actually fund longitudinal work, which at least in my experience, they're not very good at. And we might have to convince companies or governments to let us in as academics, maybe not working in industry, to be able to try things out in systems. And perhaps publicly funded software that governments often seem to struggle to produce might be a place where our communities could make a real difference. Another idea is, what if we built things more together? What if we actually had test beds that we were building, more than just collecting data out there, to actually put our techniques in practice, see how they work? Again, this is really, really difficult. It's longitudinal. You might not get an answer in a month or 3 months or 6 months, but you'd need to follow things over time and try to understand how they work when software is being grown and evolved and we really hit some of those essential complexities I referred to. So I'm hoping maybe over some fun tonight, we'll be able to start a discussion about how we can actually better study techniques that can tackle, that can try to tame the essential complexities of software development. Really what I'm appealing to is let's try and not just focus on an individual technique, but start to follow some of those techniques. Start to understand, as I said, how they can work together and how we can make a real difference in how software is going to be developed tomorrow. So hopefully we can figure out how we can do some of this longitudinal study of software in situ at scale, whether we're doing it in conjunction with people that are building other systems or whether we're actually doing some sort of reflective look back at software we're constructing ourselves. So obviously there's a lot of people I want to thank. I have some of their pictures here on the screen. I do want to thank my PhD supervisor, David Notkin. We lost David 10 years ago last month. It's still something that, I probably choke up a little bit about because I miss David. I miss his wisdom, I miss his humor, and I miss the fact that he really cared about this community and was there for so many of us to bring us into research and to keep us in research over time. I've had an amazing set of graduate and undergraduate students that I've had the privilege to work with and postdocs. Some of my PhD students are there on the screen. Hopefully some of them are familiar to you. I've had great colleagues in this community. It's been a wonderful community to be a part of. And it's a community that not only am I impressed by the insights people have and the hard problems that they attack, but just what a wonderful community is to be a part of. I have colleagues at the company that I co-founded, TaskTop, that taught me about what big software is really like. And I do want to obviously thank my family who puts up with me not being home nearly enough. But all in all, it's just been so much fun to be part of this community, to be in a place that's challenging and really open to new ideas. So that's what I wanted to say. I wanted to say that hopefully we can figure out how to start not only looking at problems in very little slices and silos, but to start putting them together, understand how we can combine them together so that we can really be the community that helps develop the software of the future. Thank you very much.
We have time for questions.
I just wanted to pick up the glove you dropped. I actually corresponded with Fred Brooks quite a bit. His paper appeared, I think, the same year at the State Shot. He and Eggerton Dijkstra were maybe the most famous, strongest opponents to visual languages. Fred Brooks actually wrote, I think I'm quoting it almost exactly, that visual languages are a favorite topic for PhD dissertations. Nothing convincing and definitely nothing of importance has ever come from them. I am convinced nothing ever will. To his defense, I mean, he's no longer with us, after corresponding with him, he essentially thought about flowcharts and things like that. Interestingly, so these are two, as you said, luminaries, both Turing Award winners. Two other famous Turing Award winners, Milner and Hoare, both much later on decided to build visual languages of their own. You can look them up. But I agree that Brooks's paper was remarkable, and I second Gail's recommendation. Go and read it. It's a wonderful piece of work.
And I also recommend reading the 1995 one, because I think he talks about that interchange with you in the paper. So a wonderful thing to read now. Thank you.
Okay, Gail, congratulations and thanks for a wonderful talk. For one point, you said we really need to build our own system to regain the first-hand experiences. I think the question is how, as a community, as you know, a lot of things would happen when the incentive system is in place. I think as the current research community, let's look at our PC of ICSE. How high percentage of the PC member actually wrote non-trivial amount of the code, right? I think for new generation students, I mean, with the culture, of course, with a lot of data around now, ChatGPT, it's faster for you to just be an observer rather than the doer. I think like for a lot of points you mentioned, I fully agree. We really need to get our hands dirty to have a lot of experiences and then have the observation. So I think my question is how? Do you have any concrete ideas? Thank you.
Yeah, I mean, thanks for that question, Tao. I think it is not that we have to build our own things, but I do think that we have to be more in connection with either the people who build them or in getting involved, like I said, maybe in publicly funded research, publicly funded systems that get built. So we can be the observers. We don't necessarily have to be the doers, and it wouldn't be everyone in the community, because we have people that are very strong theoretically. We have very strong people that are building things. But I do think that we need to start making more of us a connection to how software actually looks when it's being built, when it grows, when it gets ugly, and understand how we as a community can bring those insights back into our papers. I think we have to do more of that together, and I think we've maybe swung the pendulum a bit more to individual results, a little less away from the big system developments of the past, and we have to find a balance in there somewhere.
Maybe I'll follow up on that. I think my implication was that if you look around the PC discussion or PC reviews, right, we may not show enough appreciation on the so-called system side of the contribution or engineering side of the contribution, which has been quite highly emphasized and appreciated in the system community, like operating system, or like even in the computer architecture community, to my understanding. So then naturally, like when we talk to students, oh, have you talked to the actual target user of your system and to see how they feel? They may just say, no, I haven't. I mean, I have just done enough to get the paper accepted, right? And for the actual mileage, it's not appreciated by the community. That's why I mentioned this incentive system is very important.
So I do think the incentive system is very important, and you know what? I hesitate to say we have to start some new ways to recognize this kind of work, because it's already going on. But we have people focus more on small, incremental publishable units in general than we do in recognizing the long-term, larger impacts. And I think as a community, we can decide to do more of that and actually recognize more of the kind of work that's going on and invite it in so we can learn from it.
Thank you.
Hi, Gail. Thank you very much for the talk. Very, very nice and interesting, and I agree with a lot of the things you said. One of the things you said was that we've got quite good at understanding the artifacts on the technical world, and perhaps, you know, we need to focus more on the social side. And when you talked about the social part, you talked about people and not about organizations. And I was wondering, you know, my feeling is that organizations actually play a big role. They have big agendas, and they set the agenda, the research agenda, the technology agenda a lot. So how much of that should we be looking at?
So I guess I think of the organizational issues more in terms of, you know, the way that people, the way that companies organize their teams has an incredible effect on how the software gets produced, what the software ends up looking like. We don't look at that very much anymore. Whether or not the incentive structures, that starts to get into corporate issues that I think can be harder for academics to go in and look at. But I think there's smaller steps that we can take to start getting more into that social side. But great question, Seth.
My question may have been answered when you talked to Tao, but I'm still going to ask, because I want to ask you to talk to the authors of papers, not the reviewers. It's about the context. I remember my first DSE paper was a result of 3 years of work, a longitudinal study with the same company, where we studied improvements in the requirements processes. And we thought that introduction of one process would solve all the problems, and it would be an easy paper to write about. It was about every other thing that was going on, the way they were testing the software, they were collaborating with customers, with other processes in the company, what tools they were using. So it was really the context that surrounded the implementation of new things in the company. But it took 3 years to collect data and publish. So my question is, how do we motivate authors to not slice pieces of their research so that they publish every year 15 papers, to have that patience to publish something that is of a bigger impact?
That's a great question. I mean, it obviously starts with so many things. If it's academia, it's promotion and tenure process. We can go through grants, the whole 9 yards, right? However, we don't make any distinctions in our community really that much about being able to describe something very long and large and a little messy. Sometimes that's hard to get accepted. Sometimes you don't have the space or the richness to be able to describe that versus something that is more, shall we say, cut and dry or fits in a particular mold. So I think we can look at what we ask papers to be as part of considering this. I think it's also one of those things that as you get maybe later in your career, it's easier to think about doing. Because when you're early in your career, there are different pressures, and we're not going to change the whole system. But over time, there might be places where you can start being part of one of these longer projects and work it out through time. When I look back at our individual research results, and I'm really proud of many of them, I decided not to talk about them, because it's like, well, we've talked about them. We could talk about them again. But really what we need in the community is to start thinking about what are the questions that we are really not asking that we should be expected to have answers for. And if I'm speaking to somebody in government, it's reasonable for them to ask me, this collection of techniques, how have they worked out in practice? Some people in this room will have great answers, not everybody will, but I think we need to do better in showing that we are the place that will give you those kinds of answers.
Maybe we get one last question.
Hi, thank you so much for your questions. I'm a PhD student. I have still 5 years to complete the PhD, and the things you are discussing is too broad for a PhD student to think, because we also, I guess you partially answered my question, because there are a lot of pressure to have few publications so that you can defend your thesis. And but do you have any suggestions how to think broader? Because I sometimes my advisor asks me, what is the bigger problem that you're thinking? And I don't want to think bigger because it takes so much time and energy and patience, and I want to publish. I think this is the problem with most of the PhD students. So how do you, I mean, if you have any suggestions how we could optimize like both sides in thinking the bigger picture and also like publishing and, you know,
Yeah, great question. I think if we focus on the problems that are really difficult in software development, there's often a way to take your result and try it somewhere in actual industry. It doesn't always work out. I had the luck of being able to do that for my PhD, but the reviews for my PhD work were always, it's a really simple idea. Maybe it's too simple. It's like, but it's simple enough to try, and it makes a difference. So I think the more that we can get down to the true essence of a problem, look at state charts, right? It got down to the essence of a problem, and then you can start applying it in many ways. That's a hard thing to hear as a PhD student. I have these arguments with my PhD students all the time. How do we actually get down to what is the question that you're trying to answer? How can you push it through? And when you have that push through results, I would say in my experience, it's always made a big difference to be able to say it actually, this is what is going to be changed, and I can show you how it can get changed. But happy to talk with you again later. I'm standing in between you and dinner. So.
Let's thank Gail again and congratulate her for an insightful talk.